Welcome. This is Module 1, Task 5. I'm going to review the solutions, and I just put them together just to make it a little easier to see. The first one, we see we've got a function here that is actually two different functions, right, based on the domain. And I've graphed that in green, and what you can see is you can see that if you were to look at y equals x, you can see that both functions are symmetric around y equals x. So symmetric around y equals x. So therefore these are inverse functions. The next one here, you've got a slope of a over b, b over a, 0c, c0. You can see it's swapped. If you were to graph that with the a over b and b over a, you would also see that they are symmetric around the y equals x. The third one, if you were to create a table with some of these values, when x is equal to 3, f of x is 12, whereas in the other function, if x is 12, f of x is 3. Same thing with if x is 4, f of x is 19. In the original function, 19 gives you 4. So you can see that it's inverse because the domain and the range are swapped. On this one, I went ahead and graphed this in blue. Again, you can see, given the graph, you can see it's symmetric around y equals x. Okay, and yeah, and then this one over here, if you created a table using this function here, right, you can see when x is -2, y is -4/3. Here, when x is -4/3, y is -2. Also true for the other points, so the domain and range are swapped. Here you have a log function and an exponential. By definition, these are two inverse functions. Over here, when you look at -5 cubed, you get -125, okay? And so each of these are cubing the x value. Here, if you start with the y value, -2 cubed gives you -8. 4 cubed gives you 64. So you can see that this is the reverse of this function over here. Looking at the next one, if you sorry about that. Okay, if you go ahead and you take this graph here and you transpose it on the original graph over here, and you draw your y equals x, you can also see the symmetry between points here. Okay, this is again looking at a exponential function. And then over here, same type of thing. If you take this exponential function, which is 5 to the x, and you graph it, and you set your y equals x, you can see this black function, which is a logarithmic function, which we'll talk about later, and the purple are inverses. Same thing here. If you were to write this as a linear 5 plus 3x and graph it, and over here, using point slope 1/3 of x minus 8 plus 1 and graph it, then you would also have a let's put this in here. You would also have the symmetry. Another way would be algebraically. Let's look at that. So if we swap the x and the y here, the independent and dependent, we could say x equals 5 plus 3y. Let me use a different color here. And if you subtract 5 from both sides, you have x minus 5 equals 3y. And if you divide both sides by 3, we have a y, which is going to end up being the, what's going on here? Just froze on me here. So the function, the inverse function, making it hard. It's going crazy here. Anyway, you could algebraically show that those two are the same there. Okay, let me see if I can get this going. I think something's wrong with my stylus, so I'm not able to do this. So you could say x equals 1/3 y minus 8 plus 1. So that's x minus 1 equals 1/3 y minus 8. So that's 3 times x minus 1 equals y minus 8. So ultimately you have y equals 3 times x minus 1 plus 8. And we're showing that this is the inverse of this function. So we get 3x minus 3 plus 8, which is 3x plus 5. Okay, so that would be the inverse of that function. And that is the same function, 3x plus 5, that we had on the other